We're going to talk about sum and difference identities here for sine and cosine. And so these are the 4 sum and difference identities. We're not going to figure out where they came from. That's a different video. But we're going to talk about how to use them. And so these are the 4. If you need to write these down, I'd pause the video right now and write these 4 identities down. And so if we look at the identities we have so far, this is kind of what we've been using. We have the top portion, or I guess the top 3/4 of this is all stuff that we've talked about already. And kind of called this our toolbox for trig identities. And so a couple more that we can come up with are the 4 listed at the bottom here that were on the first slide. And there's a few more that might come up when you're talking about trig identities. There's called double and half angle identities. Also tangent of, or tangent sum and tangent difference, kind of like the sine and cosine difference. All of those can be derived from these yellow ones at the bottom here. So this is kind of our new modified toolbox of identities that we can use to prove trig identities. And what we're going to do is we're going to use these bottom yellow identities to answer a couple questions. So we're just going to run through 2 examples and solve them 2 different ways. And then we're going to do one more kind of proof at the end, and that'll be our video for this. So first one says sine of 75. And what I'm going to do is just kind of enlarge these so that we can see them a little better. There we go. And so what I want to do is figure out each of these and show you that you could use either the sum or the difference formula. It all depends on how you see 75 in this case. So if I'm using the sum formula, I do sine of 75. This is going to be the sine of 2 numbers that add up to 75 degrees. So I would do 30 degrees. It's supposed to be a 30. Let's try that again. And 45. And the reason I chose 30 and 45 is because I know those 2 values on the unit circle. I wouldn't choose 60 and 15 because 15 is not something I'm familiar with on the unit circle. So I'm trying to pick something that is a multiple of 30 or a multiple of 45. Those are the values on the unit circle that I'm familiar with. So for this one, I'm going to be using the sum sine formula. So this is going to be the sine of, we'll call 30a and 45b in this case. So it'd be the sine of 30 times 30 degrees times the cosine of 45 degrees plus the cosine of 30 times the sine of 45 degrees. And so then we can just use our unit circle. So if I think about where these values are on the unit circle, 30 would be this short skinny triangle. The x is √3/2. The y is 1/2. So for the sine of 30, that's going to be 1/2. The cosine of 45 is √2/2. And if you forgot that one, I'll just draw it quickly here. The 45-degree angle, the x and y are both √2/2. Then the cosine of 30 is √3/2. And the sine of 45 is √2/2. So if I do 1/2 times square root of 2/2, I get square root of 2/4. Plus the square root of 3 times the square root of 2 is the square root of 6. And that would also be over 4 because 2 times 2 is 4. So we have our answer, √2/4 plus √6/4. Or you might see it written as √2 plus √6 all over 4. Either are acceptable answers. You will typically see it written as the second thing, but both would be acceptable. Okay, so what if we are doing difference instead of sum? So we should get the same answer. And when I set this up, I would do the sine of two numbers that subtract to give me 75. So there's an endless number of possibilities here, but I would, what's coming to mind first is 120 minus 45. When you subtract those, you get 75 degrees. So I would just do the sine difference formula that's up here that I'm putting a green box around. So that's going to be sine of 120 times the cosine of 45 minus the cosine of 120 times the sine of 45. All right, 120, if I look at my unit circle, is this triangle right here. The x, or the cosine, is negative 1/2. The y is root 3 over 2. So the sine of 120 is going to be root 3 over 2. The cosine of 45 is root 2 over 2. Minus the cosine of 120 is negative 1/2. And then the sine of 45 is root 2 over 2. And so when I simplify this down, I can probably give myself some room here. I get square root of 6 over 4 minus negative square root of 2 over 4, which is root 6 plus root 2 over 4. And we should have gotten the same answer, and we did. It's just written slightly differently. But they're the same answer because they both are the sine of 75. And so this would be considered our exact answer for the sine of 75. Okay, let's do the same thing for cosine. Chances are, if you can do these two and they make sense, then the next two should probably make some sense to you as well. If you feel like you get it, then maybe just skip ahead a little bit and look at the last example that I do. But cosine of 165, if we want to do the sum, we could do, we could rewrite this as the cosine of 120 plus 45. I'm familiar with both of those on the unit circle, so I could do that. And so if I'm using cosine addition, I would use the bottom left trig identity. It's going to be cosine of 120 times cosine of 45 minus sine of 120. Oh, that's a 120 there. Sine of 45. And the cosine of 120 is going to be negative 1/2. Cosine of 45 is square root of 2 over 2. The sine of 120 is going to be square root of 3 over 2. And the sine of 45 is root 2 over 2. And so we get negative square root of 2 over 4 minus square root of 6 over 4. Or, as you could probably guess, it's going to look like negative root 2 minus root 6 all over 4. And then if we did this using a difference formula, we would be using cosine of a minus b. So I would just do figure out what two things subtract will give me 165. And so that would be, let's see, 210 minus 45 maybe. So cosine of 210 minus 45. So I would just do the one that I circled in pink up here. It's going to be cosine of 210 and then times cosine of 45 plus sine of 210 times sine of 45. Sorry about this penmanship here today. I have a feeling my computer's getting a little overloaded right now. So the cosine of 210, that's going to be the x value at 210. That's going to be negative square root of 3 over 2. Cosine of 45 is square root of 2 over 2. Plus sine of 210 is going to be negative 1/2. And sine of 45 is root 2 over 2. So if I scroll down here, I get negative square root of 6 over 4 minus square root of 2 over 4. And that's the same thing that we got up above. We got, so negative square root of 6 minus square root of 2, all of that over 4. And this one is the same as that one, even though they do look slightly different. The tops are both negative, so you'll get the same value if you punch that into your calculator. Okay, so for the last example, this is called the double angle identity for sine. And this says, what is sine of 2 theta? And so what I'm hoping for us to do here is to use these identities that we've looked at and figure out how can we figure out what is sine of 2 theta. Well, the trick to this is we need to realize that 2 theta is theta plus theta. So when I say sine of 2 theta, I'm really saying the sine of theta plus theta. So what we're going to do is just use the sine sum identity, and then we're just going to plug in theta for both A and for B. So what this is going to look like is sine of theta times cosine of, cosine of theta plus cosine theta times sine of theta. So since A and B are both the same, you just put theta in for both A and in for B. And so both this thing and this thing are both sine times cosine. So we can just rewrite this as 2 times sine theta cosine theta. And so this would be the sine of 2 theta. This is our another identity that we have come up with here. So the double angle identity, we call this for sine, would be that. So we're not going to do the one for cosine. You could try to figure that one out on your own. It's very, very similar to this, but I just wanted to show you one for sine.